Thank you for joining me for this video. I apologize I have to miss school. But again, this way you can still cover all the FRQs from Chapter 6 that you're going to need. So a couple tips as we're diving into these FRQs. Obviously, we're still mainly talking about probability situations here and expected value. Now for probabilities, if you're using a special distribution, normal, binomial, geometric, any of those, again, make sure you label it as such, because if you label what type of distribution it is, it justifies all the math that you're going to do later on. Also, though, if you're going to use expected value or standard deviation, I kind of showed you those formulas yesterday. Make sure you show plugging them in, but then, of course, you are free to use the calculator for things like standard deviation, which are awful to get on your own. So, let's dive into our first example and start working through it. So, our first example, a charity fundraiser has a spin the partner game that uses a spinner like the one illustrated in the figure below. A donation of $2 is required to play the game. For each $2 donation, a player spins the pointer once and receives an amount of money indicated in the sector where the pointer lands on the wheel. The spinner has an equal probability of landing in each of the 10 sectors. So let X represent the net contribution to the charity when one person plays the game once. Complete the table for the probability distribution of X. All right, so when they spin the wheel, they earn either $0, $1, or $10. Now notice X represents the net contribution to the charity, okay? So what that means is for the charity to get $2, it means the person won no money back. Okay, so it means that the person got a 0, okay? So how many zeros are up there? Well, I count 6 out of the 10 sectors. So the probability is going to be 6 out of 10 or 0.6 that the charity gets to say or gets to keep the $2, okay? Because the person won nothing. For the charity to keep $1, again, what that's talking about is the person won $1, okay? So 3 out of 10 have the person winning $1. So 0.3, 30% of the time, the charity is going to get $1 back. And for the charity to be down $8, obviously means the person won 10, okay, because they gave 2, but then they won 10 of that back, so the charity is giving up $8. And again, that is one of the 10 sectors. So we're talking about 0.1. All right, so that's it for A. But let's talk about the charity would like to, or sorry, B, what is the expected value of the net contribution to the charity for one play of the game? All right, expected value. So this again is a formula on your formula sheet. So I can't show you the formula sheet. So instead, I'm just going to write up here what that formula would be. Okay, so the expected value formula that you're looking for in your packet looks like this, summation of xi, pi. And again, we talked about this a lot yesterday for the multiple choice. So basically, you just take each value, so 2 times its probability, then plus the next one times its probability, and the next one times its probability. Okay, again, this symbol right here means add them up. So take each value times its probability and add all of those up. When you do that, 2 times 0.6 plus 1 times 0.3 minus 8 times 0.1, we're getting a net contribution of 70 cents. Okay, so in general, we're noticing each time a person plays, the charity should be getting about 70 cents per play in the long run. Okay? Now, the charity wants to receive a net contribution of $500 from this game. Okay, so to receive $500, well, let's talk about that math. Okay, so I'm going to erase this. But what we're talking about is they're expecting to get 70 cents per time that they play. Okay, and so overall, they're going to want $500. So this is actually just algebra, right? They expect to get 70 cents per time playing, and overall they want to get 500. So in the end, if you take 500 divided by that 0.7, oh, I'm sorry, they're going to have to play 714.3, rounding that up. They're going to have to have 517, or said that backwards, 715 times playing. Okay, so let's move on to part D. So part D says, based on last year's event, the charity anticipates that the Spin the Pointer game will be played 1,000 times. The charity would like to know the probability of obtaining a net contribution of at least 500 times in 1,000 plays of the game. The mean standard deviation and the net contribution of the charity are 700 and 92.75 respectively. Use the normal distribution to approximate the probability that the charity would obtain a net contribution of at least 500 in 1,000 plays of the game. Okay, so here it says to approximate this distribution as normal. So they're saying approximate it as normal, where you get $700 with standard deviation 92.79. Okay, they're saying that this models approximately that distribution. And we want to know the probability in 1,000 times playing. We want the probability getting at least 500. Well, again, normal, they're actually bringing this back, right? So if we're assuming it's normal, we have this observation. We want 500. We want the probability. Well, we have a pit stop to take first, don't we? We need to figure out that z-score first. So, oh, I'm sorry. We're curious about the observation of 500 minus the mean of 700, standard deviation 92.79. So negative 2.16. And we, of course, are going to use normal CDF from there. We want at least 500, so we're going to be taking that negative 2.16 and going upward. Okay, so normal CDF, negative 2.16, up, is going to give a probability above 0.9846. So if they actually get 1,000 plays in of this game, again, we're in good shape. There's over a 98% chance they're going to get the $500 that they're looking for. All right, our next one. So looking at our next FRQ, the weights of red delicious apples are approximately normally distributed with a mean of 9 ounces, standard deviation of 0.75 ounce. An online gift store sells gift boxes containing 5 red delicious apples. At the time of packaging, 5 red delicious apples are randomly selected and packaged in a box. Okay, so they wanted to describe the distribution of the total weight of those 5 apples. So describe, again, hopefully you know that means socks, right? Now, they talked about this being normally distributed. So if you combine normally distributed things, the shape is still going to be normal. So combining normal distributions will lead to a normal total weight distribution. So we've covered the S, the shape of socks. Outliers, again, when we're talking about distributions such as these, we never really cover the outlier piece. Let's talk about the center. So each one has a mean weight of 9. Okay, so the new mean, if we have 5 of those apples, the new mean is just going to be 5 times that 9. Okay, we would expect them to weigh 45 ounces total because each one is expected to weigh 9. Standard deviation, though. Standard deviation, again, that we can't combine standard deviations, but what we can combine is variances, right? So we have a standard deviation of 0.75. Well, we have to turn that into a variance, right? Because again, we can't combine standard deviations. We can combine variances. Specifically, we have 5 of these apples we're bringing together. Right, so really we have 5 of those variances. But we don't want a variance. In the end, we want it back as a standard deviation. So again, ultimately, we're going to have to square root that whole thing. So when you type that in the calculator, square root of 5 times 0.75 squared, I'm getting a standard deviation of 1.677 ounces. Okay, so again, the big idea here, standard deviations do not combine, variances combine, then you have to square root that to put it back to a standard deviation. So what's the probability that the total weight of the 5 randomly selected apples will be less than 42 ounces? All right, well, again, we're talking about something that's normally distributed, centered at 45, standard deviation 1.677. So again, our general approach with a normal probability is going to be this idea still, right? Once again, we're going to find a standard deviation, we're going to find a z-score so we can finish this off. So the observation we're curious about is 42 minus the mean divided by standard deviation. So -3 divided by 1.677, we have a z-score negative 1.79. All right, and we're talking about less than, right? So when we plug this in to normal CDF, we're going to be starting negative going up to that z-score. So I'm going to start negative 1,000 up to negative 1.79, and we're going to get a probability of about 0.0367. So under a 4% chance that the total weight is going to be below 42 ounces. All right. So let's keep moving on to part C. So part C now says the combined weight of the packaging material and the box in which apples will be shipped is always 10 ounces. Well, W represents the weight of the complete packaged gift box, which consists of packaging material, box, and 5 randomly selected apples. What are the mean and standard deviation of W? So W will still be normal, right? Because if I just take a normal curve, I add the same amount to every value, well, still normal. Now, the cool thing is it says is always 10 ounces, right? So basically, I'm just always adding 10. There's no variation to the packing materials in the box. It's always 10. So the new mean is going to be the 45 ounces we had before plus the 10 for that new packaging material. So the new mean is going to increase to be 55. It's going to increase by 10. Now, here's the cool thing. Standard deviation. So remember, if I pick up that whole distribution and literally just add 10 to it, it obviously moves the center of my distribution. That's why we saw the mean increase. However, the standard deviation, if I'm just shifting the whole thing by 10, the standard deviation actually isn't changing. Right? It doesn't change from adding a constant. Right? I'm not adding anything to the spread. I'm literally just moving the distribution around. So it's still going to be that 1.677 ounces. The standard deviation doesn't change with addition or subtraction, right? All right. So our next one is a little bit of a beast. So let's dive right in. So, an important method for controlling the spread of H6N2 influenza, bird flu, virus in chickens is having a procedure to determine whether chickens are infected with the virus. It is common to apply a procedure called the ELISA test to measure the concentration of anti-bird flu antibodies in a blood sample taken from a chicken. If the ELISA test reveals high enough concentration of antibiotics, the chicken is said to test positive, and it is classified as infected with the virus. Otherwise, the chicken is said to test negative and is classified as not infected. However, the ELISA test is a complex procedure that is not always accurate. One type of mistake, a false positive result, occurs when an ELISA test gives a positive result for chicken that is not infected. A second type of mistake, a false negative result, occurs when the ELISA test gives a negative result for an infected chicken. Considering the possibility of false positives and false negatives for tests on individual chickens, veterinarians have developed the following procedure for determining if the H6N2 virus is present in a large flock of chickens. So what they do is they randomly select 10 chickens from the flock, perform the ELISA test on each of the 10 chickens, conclude that the virus is present in the flock if at least 3 of the 6 chickens test positive. So suppose a veterinarian applies a procedure to a flock of 100,000 chickens at a commercial egg production farm. The ELISA test is known to have probability 0.05 of producing a false positive and a probability of 0.1 of producing a false negative result for a single chicken. All right, so if no chicken in the flock is infected with the H6N2 virus, what's the probability that the veterinarian will conclude that the H6N2 virus is not present in the flock? Show how you got your answer. All right, so we have two things here, right? First, if the chicken actually has the virus or not, and then what the conclusion is of the test. So here, I think a tree diagram is a great way to model this information for us. So in 6, they're saying no chicken in the flock is infected. Okay, so here, infected or not, they're saying there's a 0% chance of it being infected. They're all not infected. Okay, but then we still have the results of the test, right? What does the test say? Well, the ELISA test has a probability of 0.05 of producing a false positive. Okay, so a false positive meaning determining that it has the disease when it actually doesn't. and a probability of 0.1 of a false negative. So it has the disease and it doesn't determine that, right? It comes back as not sick. All right, so and we want to know the probability that he'll conclude that the virus is not present. All right, so to determine that it's not present, well, again, we need to figure out what's the probability of it coming back negative or of it coming back positive, right? Because if too many come back positive, we're going to have a problem. So to come back positive from the test, we're talking about this or this, right? So if this or this could happen, again, you multiply down the branches, but you add in between them, right? So this is the probability, 0.05 is the probability of getting an infected chicken, okay? Now they talk about they're going to do this for 10 chickens, okay? So for 10 chickens, each one has a probability of 0.05 of coming back with a positive test, okay? And if at least 3 of those 10 chickens end up with a positive test, then he's going to say that the virus is present, okay? So what we're looking for is actually for the virus, for him to conclude the virus is not present, we want them to have the outcome in 2 or less chickens, right? It being present in 2 or less. Now, if you notice, doesn't this sound binomial, right? Counting successes out of a total. So we're counting the number of ones that come back with the virus indicated out of a set number. So this is binomial, right? Binomial, 10 trials and a probability of 0.05 of success, of coming back saying that there is a positive result, right? And what we want for, oh, I'm sorry. We're talking about the virus being present. I'm sorry. I was reading the wrong one. All right. So here, the virus being present, I'm sorry, that would legitimately take 3 out of the 10 chickens. So we'd be looking for at least 3 being infected, right? So if X is the number infected, we would need at least 3, right? So we want to find the probability of coming back with at least 3. Now, if you remember, there is a situation here, right? The situation being the calculator doesn't understand that, right? The program is always in terms of less than, right? So remember, we have to switch this. Being greater than or equal to 3 is the opposite of being less than or equal to 2. All right, so now when is cumulative like this, right? Less than or equal to, I'm hoping you remember that is our binom CDF situation, right? So binom CDF, we have 10 trials, probability of 0.05 and 2. So the probability that he's going to find that is present, well, let's go type that in, shall we? So 1 minus, I can type that in. Now, if I go into distribution, remember that is where binom CDF is, okay? So we have 10 trials, probability 0.05 of success, and we're looking for 2 or less, okay? So the probability that he determines that the virus is there when absolutely none of them have it is going to be about 0.0115. So about a 1% chance. So this seems pretty effective, doesn't it? Okay. So let's go back and do the next one. So the next one says, part C, if every chicken is infected, what's the probability that he'll conclude that the virus is not present? All right, so this time these are going to be opposite. Every single one of them is infected, right? And none of them are clean. Well, this time, if I want to determine the probability of getting a positive result, well, when I do it this time, just like I did last time, this time I have a probability of 0.9, right? If every one of them is infected, I have a probability of 0.9 of getting a positive result, okay? And again, if at least 3 of those 10, if I take 10 chickens, if at least 3 come back as positive, I will conclude that it is not, that the virus is present. Now this time though, this time we're going to determine, to find how likely is it to determine that it's present. Well, same thing, right? Same story. This is going to be binomial. We're still counting the number of successes, but this time the probability of success has changed. This time it's a 0.9 chance of determining that a chicken has the infection. To determine the virus is present in the flock, well, we're still looking for the probability of getting 3 or more chickens. Also, same thing though, we can't determine greater than, so we're going to want to do the exact opposite of that. So the exact opposite of being 3 or more is being 2 or less. So this time it's that same idea, the same CDF command, because this is cumulative. However, this time the probability has changed, right? This time is 0.9. So if I go back into the calculator, I'm still doing the 1 minus. If I go binom CDF, this is the only difference, right? My probability. Everything else is the same that I'm doing. So here, look at this. A 0.99999 chance that the test is going to do its job. Okay, so 0.99, I'm not going to write all that. Just, you can write that down. So this means the test does a pretty good job, right? If everything is infected, there's almost 100% chance the test is going to do its job and figure out that there is the infection. Okay, so we've seen both extremes, and on both extremes, it looks like the test is doing its job. Let's talk about the last scenario, part D. If 20% of if the flock are infected and 80 are not, what's the probability that he'll decide that the virus is present in the flock? So again, this is almost the same situation. But this time, we're going to say 20% are infected, 80% are not infected. So if we want the probability of getting a positive test result, 20% are infected, or it could get a positive result even if they're not infected. Okay, so I type that into my calculator, 0.2 times 0.9 plus 0.8 times 0.05. And I get a probability of 0.22. So for any randomly selected one, there's about a 22% chance that it's going to come back with a positive test result. Well, again, this is going to be a binomial situation. I'm checking 10 chickens. Each one is a 22% chance of infection. And again, to determine that there's the infection, I need to find the probability of getting 3 or more successes. Again, same as last time. My calculator can't do that, so instead I find the exact opposite. So the nice thing is for this particular problem, once you've gotten B, you've gotten all of this. Oh, binom, CDF, 10.22, and 2. So again, once you know how to do one piece of this, you can do every piece of this. So now just type it in the calculator. The only thing I have to change is that probability. So if 20% of them are infected, there is a 0.3831 chance that he decides that this virus is present. All right, so again, I like this one because I think it really masterfully shows how they can work binomial into a problem, right? It's probably going to be subtle. If it pops up, it would be popping up in a very subtle way into the problem. And here, again, this kind of clues you in. Okay, you're talking about number of successes out of a total. That kind of clues you in that ultimately this is going to be a binomial setting. All right, one more question, and then we will call it good for this video. So a test consisting of 25 multiple choice questions with 5 answer choices for each one is administered. For each question, there's only one right answer. Let X be the number of correct answers if a student randomly guesses from the 5 choices for each of 25 questions. What is the probability distribution of X? All right, so this one, again, we were just talking about this, right? A set number of trials counting successes. Well, look at X. We have 25 questions, right? And each one, there's a 1/5 chance of getting it right. And we're counting the number right. So part A, the distribution of X, I'm hoping you can see is actually binomial. Is binomial with probability of success of 0.2 or 1/5, and n equals 25 trials because there are 25 questions. So again, I'm hoping that makes sense to you, especially after the last one we were just talking about number of successes out of a certain number of trials. When that's what you're counting, you are talking about a binomial setting. All right. So once we know this is binomial, let's move on to the next piece. So this test, like many multiple choice tests, is scored using a penalty for guessing. The test score is determined by awarding 1 point for each question answered correctly and deducting 0.25 point for each question answered incorrectly and ignoring any question that is omitted. That is, the test score is calculated by the following formula. So 1 times the number of correct answers minus 0.25 for the number of incorrect answers plus 0 for ones that you don't answer. Suppose a student knows the correct answer for 18 questions, answers those 18 correctly, and then randomly from 5 choices for the other 7. Show that the expected value of the student's score is 18 when using the scoring formula above. All right, so we're talking about expected value here, their expected score. All right, so their expected score. Okay, well, the expected score is 1 times the number that they get right. Okay, so we know for sure that they have 18 right. But then there's 7 unaccounted for, right? 7 that they're guessing on. So I'm going to call this the expected value plus the expected value of x, okay? And I'm going to let x be binomial where there's 7 trials and a 1/5 chance of being right, okay? Because if I add that expected value on, that's going to be the number of points that I'm going to receive for being right. 18 plus how many we'd expect to get right based on that binomial distribution. Well, then it says to subtract off 0.25 for each wrong. Well, the only ones we can get wrong are the remainder from the 7, right? So if we're expected to get a certain number right, then the opposite of that is what we would expect to get wrong, right? Okay, so, and then we're not leaving any blank, so we don't have to worry about adding any of those on, and it wouldn't matter because blank ones are 0 anyway. So again, for now, I'm hoping this makes sense. 18 plus however many we expect to get right, minus 0.25, and then the rest of those 7 are what we would expect to get wrong. Okay, and again, that x that I'm using is, I'm going to call that binomial of 7 trials. Okay, now on the formula sheet, you're going to see below the probability section, okay, it talks about if x has a binomial distribution, then the mean of x is going to be the number of trials times 0.2, or times the probability. So if we take 7 of these things, each with a probability of 0.2, we would expect to get about 1.4 right. Okay, 7 times that 0.2. So if this is what we're expecting to get right, that is actually our expected value for those remaining 7. So I'm going to have 1 times the 18 plus, we're expecting to probably get 1.4, minus off that 0.25, and again, the rest of those 7 are going to deduct points for us. Okay, you plug all that in the calculator, you get 18, and again, you know that's what you should be getting. It says show the expected value is 18, and again, I just did that. Okay, I showed that it's 18. That one, the nice thing is in the end, you know you have the right answer because you know what you should have been getting. Now, part C. So part C says a score of at least 20 is needed to pass the test. Suppose a student knows the correct answer for 18, answers those right, and then randomly guesses for the other 7. So basically the situation we just constructed, right? And we want to know the probability the student will pass the test. All right, so here, I'm going to alter the formula that we just used, okay? So I'm actually going to scoot this up because we know how to calculate their score, right? We just came up with a point for each one that they get. So if they get X right, that's what they get, and minus the opposite of that from 7. So the rest of the 7, they lose 0.25 points for getting them wrong. And what we need that to at least be 20, right? To pass, we need that score to at least be 20. So we can determine how many we need to get right in order to pass. Okay? So what we need here, so we have 18 plus x right here. If I distribute this, you're welcome. We have a little bit of algebra here. Oops. 1.75 plus 0.25x is greater than or equal to 20. So if x is, again, the number we need to get right, now we can just solve this algebra problem. So 18 minus 1.75 is going to be 16.25. Combine the x and the 0.25x, give us 1.25x. If I subtract that 16.25 over, that gives me 1.25x is greater than or equal to 3.75, and divide by x. Okay, and if you divide by x, you're going to get 3. So basically, what I've just determined so far is to pass, you need to get 3 of those questions right. Okay, so 3 of the ones that you guess on, you need to get right. Well, again, we know that x is binomial, right? We set x up to be binomial like this. So if we need to get at least 3 right, again, we can use binom CDF to figure that out, right? Because this is a binomial distribution. We just got finished talking about in that bird flu one, though, that really what you need to figure out then is the opposite of that, right? The probability of being less, or the opposite of being less or greater than or equal to 3 is less than or equal to 2. So if we binom CDF that, again, we have 7 trials. Each one has a 0.2 chance of being right, and we need a 2 there. So 1 minus binom CDF. This time we only have 7 trials. Probability of just 0.2. And there we go. So if we guess on those last 7 questions, we have roughly 15% chance of ending up passing that test. Okay. So a lot to take in, right? I do think these are really good examples though. Now, obviously watching a video isn't quite as easy as being able to discuss it with me in class. So I hope that you'll look through this, and if there's anything that you don't understand, anything you found confusing, make sure to highlight that for me, so when we're back in class together, then you'll be able to ask me about that in person. Okay, so again, please make sure that you note any questions you have, so then we can look at it together. Otherwise, you should be working on finishing up that Chapter 6 packet for me. Now you have some FRQs to do, so please work on those and have those ready to turn in to me, and be checking your answers with my online answer key.